hello, which we're effectively doing at the moment. So hello to our attendees who are pouring in.
We're not live yet, are we?
We are live.
Oh, we are live. Hello.
Yeah, it's okay. We're live with the splash banner up, so they can hear us but not see us.
Oh, I see. Oh, I see. Oh, brilliant.
So,
well, they can't see us yet.
no, but they can hear us.
Will they be able
Okay.
to see
Hello,
us in a
George
minute?
and Barbara.
Okay, so we are live on YouTube. We are going live on Facebook. We are live on Twitter or Periscope or whatever it is.
Oh, I will send a link to people. Wait, can you send me the link on the chat or something, or so that it's a link that I can send to my boyfriend?
Yes.
You wanted to listen.
Let me move some notifications out of the way and find the right monitor. So link is. I didn't realise there were .science domains until when I was setting this up, and I love the fact that they exist.
That's so cool. I'll put it on Twitter as well.
Okay. It's good, isn't it? I missed that happening.
Right, and we do have attendees, a number of attendees, and thank you to all of you for your good evenings. And yes, we're looking forward to this as well. So, without further ado, I will take that off and put Chris on to do the introduction. You're on.
Hello, people. Thanks very much. Nice to see everyone turning up again. Yeah. So I'd better just explain briefly about Cafe Sci, which is local open science events that are supposed to be very informal, hence the word cafe. So they usually take place in a cafe, although we were just discussing that ours started out in a wine bar and then migrated to an art gallery. They can be anywhere you like, and the idea is that it's extraordinarily accessible both to attendees and speakers. And actually, we've always said that Cafe Sci should be a conversation more than a lecture. We love lectures and they're very good, very impressive. But tonight's is actually a conversation. It's a conversation between James, who's our normal host, and actually the person who set up the online Cafe Sci when we couldn't meet in person again. And he's going to be talking to Dr. Eloise Sterrance, who is an astrophysicist. And she's going to be talking about extragalactic transients. That's not how she titled it, but I looked up her biography in the University of Sheffield. An extragalactic transient. Well, I'll let her explain what they are, but they're big exploding things that are a long way away. Anyway, so Eloise is now currently at the University of Auckland. Is that right, Eloise?
That's right, absolutely. It's 8 a.m. in the morning in Auckland City now.
Which is in New Zealand.
It is.
Well done. And we all wish we were in New Zealand at the moment, but we won't say why. Well, there's multiple reasons why we'd like to be there. Yeah. But I believe you studied at the University of Sheffield and did your PhD at the University of Sheffield. So that's an interesting local connection. Lovely place, Sheffield. Always liked it very much with the hills all around it. I just want to go through a couple of things. If you touch your screen, if it's a touch screen, or look at the bottom of it, if it's a computer, you should see that there's a button for Q&A. That's question and answer. And if you write questions in there, then James, who will be conversing, but also watching his screen, will pick those up and he will then put them to Eloise. He may, with some of them, if it's appropriate, ask you if you're happy to have your audio unmuted so you can put the question live. So that's the way you communicate with us. You'll also see there's a chat button, and I've never quite understood that. That's just so that you can say, way to go, looking forward to this, great, and so on. I guess you can use it for anything else, but it chats with us, the panelists, and not with each other. Wish we could talk with each other, but we'll work that out at some later point. And the last thing is that there's a raise hand. And the only thing we really use that for is to do clapping by raising and lowering the hand. But if you want to raise your hand, I've never seen anyone do it, and I've never seen anyone actually react to it. But I guess it means I want to interrupt in some way. and we'll just deal with that when it comes up. Okay, so without further ado, I'm going to turn over to Eloise. Welcome. Thank you very much for speaking to us. Very much looking forward to this.
Thank you so much for having me. I'm so excited about these events, and doing it remotely is very new because of quarantine, but I think it's really a good idea to bring science closer to people.
And yeah, thank you for being here. Thank you for being our first, apparently, of many international speakers, and the most international, being on the other side of the world and being tomorrow. So yes, this is not running on our normal Thursday evening. If you're in New Zealand, this is bright and early on Friday morning. So particularly thank you for getting up that early.
No problem. Thank you for changing the time a little bit so that I wouldn't have to arise before the sun.
And as some of you will know, we usually encourage participants to have a drink in hand. Can be non-alcoholic, can be alcoholic, doesn't matter. But obviously
this
I'm
is
on
vodka.
Something, and Eloise is on coffee and vodka.
You know, you need your fuel for the end of the week. It's Friday. You need to make it through the end of the day. That's just how I
That's still throwing me off, and the time difference did cause a little bit of panic.
I live in the future.
So I'm going to just get started then, and we spoke a bit about this one, but I'd still like to ask it and be clear on it. You've mentioned kilonovae, supernovae, novae, and I don't know if there are any other types, but what's the difference between them? What are they?
Okay, that is such a great question, and there is so much to unpack here. The first thing to unpack is that astronomers are really, really crap at naming things in a consistent way. What happens is usually you observe something, you're like, this is new, I will give it a new name. And sometimes you think this is very similar to something because it looks the same, but it really isn't. It's a completely different phenomenon. And then you get stuck with similar nomenclature because that's just the way that people name things. And that's exactly what happened for novae, supernovae, and kilonovae. So let's start with the nova, because that's the thing that goes way, way back. And that's kind of the OG. Nova just means new in Latin. And that name is there just because astronomers looked up, they see a new star in the sky, star in quotations because it's not actually a star. And they're like, well, this is new. Nova. Makes sense. Now, astrophysically speaking, the actual phenomenon that's going there is that you have a white dwarf. A white dwarf is just the core of a sun-like star that's been completely stripped of its outer envelope because the star has died, basically. So it's not really doing anything. It's not fusing any elements. It's just really small, the size of the Earth. It's really dense, really bright. And that white dwarf has a companion that's rotating around it. And that companion is getting a little too close, just a little too close, or it's a little too big. And so the white dwarf just cannibalizes its companion and just strips its outer envelope. All that hydrogen just gets accreted onto the white dwarf. When too much of that material gets accreted onto the white dwarf, it will ignite. So it will start fusing. And that fusion is explosive. And so you get an explosion that we call a nova. The whole system just brightens up, and you can see it as a new star, quote unquote, in the sky because it goes so high in luminosity that it goes from being invisible to the naked eye or to your telescope to being visible again. So that's the nova, and most of the novae that we know about and that we study are in the galaxy, in the Milky Way, right? Because they brighten up quite a lot, but not so much that you can see it from halfway across the universe. But supernovae are a little bit different. They are the extragalactic transients that I started studying at the beginning of my PhD. Extragalactic just means in another galaxy. And so supernovae came about because in the early 20th century, astronomers started to realize that there were other galaxies in the universe. It's pretty insane to think that 150 years ago, people didn't know that other galaxies were a thing. They just saw these nebulae, these fuzzy blobs in plates and as in the pictures of space, and they were like, "What's that?" Turns out it's other galaxies. And so people found that there were other worlds out there much, much, much further away, and that the quote unquote novae that they found were much brighter than they thought. Because if you can see something from much further away, it has to be that much brighter. So because they were much brighter, they were super bright, they called them supernovae. I'm not kidding, that's kind of where that stands for. Supernova used to be hyphenated instead of being one word, but then because astronomers started using it and using it and using it, they dropped the hyphen eventually. But the problem is that a supernova isn't really a bigger version of a nova. Like some of them are, but some of them really are not. There's two main ways that you can make a supernova. And one of them is actually a little similar to a nova. That's where you have your white dwarf and it's gaining mass as well, either because it's stripping its companion, like we talked about, or because it's just merging with another white dwarf. And if it reaches a critical mass of 1.44 exactly solar masses, then the whole white dwarf basically explodes, starts burning explosively, the entire thing is disrupted, creates a lot of iron, creates most of the iron in the universe actually, goes bang. And that's a thermonuclear supernova, if you want the actual term and to Google it. Another type of supernova is completely different. It's got nothing to do with that.
I'm just going to rudely interrupt you and ask you to explain what is a solar mass.
Oh, that happens very often. Solar mass, one mass of the sun. Solar, just sol is sun in Latin and other Latin languages. That's where soleil comes from in French. So yeah, it makes sense in my French brain, but I realize that for British people, it's a little bit of a stretch. So solar mass. And here's the thing. Some people sometimes think that I'm dumbing things down to compare things to the sun all the time. I'm not. Astronomers are just like that. We're like 2 times the mass of the sun. That's 2 solar masses. We just made it an entire unit because why not? You know, these things are so big, you can't measure it in kilograms. So we actually measure stars with respect to our sun constantly. So yeah, it's not a device for Psycop. It's actually astronomy units. Anyway, massive stars, really, really big, born with at least 8 times the mass of the sun, or 8 solar masses. And these have a very different life and a very different death. So they tend to live quickly and die very young. And what's very special about these stars is that they make a lot of the elements that we need for life in the universe. So oxygen, for example, comes from these massive stars, because it is made in the stars like the sun, but it gets stuck in the white dwarf, so you don't give it back to the universe. And so you make all of these high mass elements, so oxygen, neon, magnesium, these are increasing in mass all the way up to iron in the core of the star. The problem is when you get to iron in the core of the star, you can't use fusion anymore as a fuel. That's just because of physics. I don't have time to go into it, but physics basically. You can fuse all of the elements before iron together to release energy, but if you try to fuse things beyond iron, you'll actually need to give energy to the atoms to fuse them together. So it doesn't work as a fuel. And the reason a star needs fuel is because it's really big, so gravity's pushing everything in, wanting to make it collapse. You need something to balance this gravity out. And fusion releases heat, it releases pressure that pushes everything out. That's what balances gravity. When you run out of fuel, that balance is messed up. It's completely disrupted. And so the core collapses. In about a quarter of a second, the equivalent of 1.5 times the mass of the sun condenses into an object that's only 20 kilometers across, right? So about the size of a city. That's so dense that the electrons and the protons in the atoms are forced together to make neutrons, and you just get a big ball of neutron called a neutron star. That neutron star is so dense that if one of your blood cells was the same density as a neutron star, it would weigh about the equivalent of 1 Boris Johnson. You got to admit, that's pretty dense. It's pretty dense. Sorry, dad jokes are my thing. Anyway, so you've got your neutron star in the core of your massive star. The rest of the envelope of the star is going to fall onto it a bit slower, and is going to encounter that really dense material, bounce off of it, that sends a shock wave, and that starts exploding your star, and that's where your supernova comes from. So that type of supernova, core collapse supernova, very literal, you know, because we're astronomers, is just another type of supernova. So very different phenomenon, same name, because it's similar magnitudes, so similar brightnesses. You can also see them from pretty much halfway across the universe. Pretty cool. Now, the kilonova is different. Kilonova is neutron star mergers. So we just talked about that neutron star that's left over from the core collapse supernova. Thing is, you can have two of them together. If you have a binary system, so two stars who live their life together, and they're both stars that were born massive, then both of them can...
Can we just go back to the neutron star a second? Because
yes.
I'm interested in this one.
Yes.
Is there a limit how much it can condense down, or is it infinite?
Yes. So no, it's not infinite, because if you condense further, you get a black hole. So there's a mass limit to neutron star, and we're not actually exactly sure where it is. So we think it stands around twice the mass of the sun, 2.1 times the mass of the sun at this point. But we're not exactly sure where the limit is. We're kind of stuck with theory at this point, and with observations of neutron star mergers that we've observed, and we've seen one at this point in 2017. We've seen a few others in gravitational waves, but like with actual telescopes in visible light, just the one. And so that's still an open question. As for density, it's kind of stuck at a limit that we call neutron degeneracy pressure. And so that's a whole other aspect of physics. Degeneracy is another another phase of matter. So, you've got solid, liquid, gas, plasma. Plasma is like a gas, but the electrons are completely stripped off of the atoms because it's too hot. So the electrons are like, screw you, see you later. That's what's in a star, a plasma. And on the other end of the scale, something that's denser than a solid is degenerate matter. That's where basically your particles are stuck packed as densely as they can be, and start messing with quantum physics. So we're not going to go into that, but imagine a bus and every seat is filled and everyone's standing up in like sardines, and you can't put anything in there anymore. Then nobody can get in the bus, right? So you're stuck, and that's as densely as matter can be packed. Because to be fair, matter as it stands, like around us, is mostly empty. It's mostly empty. It's very vacant. So the reason they're so dense is that they have the density of a nuclear atom. Which may not make a lot of sense, but when you think about it, 20 kilometers across and 1.5 times the mass of the sun is pretty insane, because the sun in radius is 100 times larger than the Earth. And we're talking about the mass of a city, the size of a city. So it's just unimaginable at this point. And that's why we have to rely on kind of stupid comparisons like blood cells and Boris Johnson to try and get an intuition for it, because there is nothing that compares in our daily life. Absolutely nothing. Space is amazing.
We've got a couple more. I'm going to ask the second one first because that sticks to where we are, and then go on to George and Barbara's. Is there a limit how much the singularity can condense down to in a black hole, or is that infinite?
So black holes, you can put whatever you want in a black hole. The black hole will just be bigger. There is an equation called the Schwarzschild radius, which I can try to spell in the comments and fail. You can try and Google it. And it just tells you, given a certain amount of mass, how big is the black hole, so the event horizon, going to be. Now, let's define the event horizon very quickly. Basically, the event horizon is the limit where if a photon crosses that frontier, it's never coming out. So if you cross that frontier, you'll be screwed as well, because you're not going faster than a photon. So that's where it starts being black, because the reason a black hole is black is because photons can't get out. And so you can apply that radius to pretty much anything. I did the calculation for the Earth once, and if you were to condense the Earth, the mass of the Earth, into a black hole, it would be the size of a marble, right? So that kind of tells you the kind of density that we're looking at. So it's unfathomable. Again, really unfathomable.
And I saved this one for next because I think this goes back onto kilonovae. How do elements heavier than iron get created then?
Kilonovae. So there's loads of things to say about nucleosynthesis in the universe. Nucleosynthesis is the synthesis, so creation of nucleus, so atoms, stuff like that. And kilonovae is an important piece of the puzzle. So kilonovae is where you make, I'm going to say what kilonovae is in a minute, but I'll just tell you what they make since that's the question. They make silver, platinum, rare earth elements, which if you look at the periodic table of elements, they're much, much heavier than things like oxygen, iron, and stuff like that. And the reason they're rarer is because the events that make them are much rarer as well. And so the kilonova is where you've got neutron star mergers. So your two neutron stars are in an orbit around each other, and eventually they will merge. And the reason they merge, is because gravitational waves, which is the thing that LIGO and Virgo can observe. And so a brief recap on gravitational waves. There's the space-time continuum, and anything with a mass warps it a little bit. And if you've got a really dense mass, you warp it a lot. And neutron stars have that property that they are very massive in a small space. And it's like digging a bigger well inside the fabric of space-time. And so if you've got these two rotating around each other, they will create ripples that then propagate in space. And we can measure them. So the thing is, if you're creating waves, you have to expend energy. That's kind of the thing about the universe. Energy doesn't just happen to appear. It has to be taken from somewhere, and it's taken away from the orbit of the system. So the two stars rotating around each other, which means that they are going to get closer and closer together as they create these ripples in the fabric of space-time. So eventually they merge. And when they merge, they make a big mess. They create a big explosion we call a kilonova. The reason it's called a kilonova is back to the nova. A bunch of people made some calculations a while back, quite a while back actually. And theorists thought that a kilonova would create about 1,000 times the energy of a nova. And 1,000 is kilogram, 1,000 grams, kilonova, 1,000 novae. I don't know if that number is true anymore, but we're kind of there and stuck with the nomenclature. That's how classification works in astronomy. You call it something and you're stuck with it. But you know, they are very bright, but not as bright as the supernovae. There's just not as much material there. But they do make the same explosive mess. And in that explosive mess, because there's a lot of energy, you can bang atoms together. And one thing that's very, very important in the neutron stars is that there's a lot of neutrons. You know, who would have thought? There's a lot of neutrons. And so there's a different process that happens in those kilonovae that can't happen in the supernovae, which we call the R process. It sounds really fancy. It isn't. R stands for rapid. It means shooting neutrons as quickly as you can at your nucleus so that they stick before the nucleus is like, I'm unstable, I will decay, you know? So if you can do that through a bunch of neutrons at nuclei before they decay, you can reach elements that are stable, but you wouldn't be able to do that if you were giving the neutrons slowly because they would decay before they would reach these steps. And so that's why you can create things that are much heavier, is because you reach these islands of stability in the periodic table of elements. As for things that are much heavier than that, well, they're just very rare processes, and good luck. There's a beautiful periodic table of elements that I'll try to find that you can Google. It's if you Google origin of elements periodic table, you'll find a periodic table that is color coded according to where things come from, like supernovae, kilonovae, old massive stars and stuff like that, and it's a really good graphic. Let's check the questions.
Sorry, I was just testing dinner there.
Tasting dinner. What are you having for dinner?
Smoked trout.
Oh, nice.
Right. One question is kilo or killer novae?
I don't know.
I'd guess it depends.
I'm not a native.
Standing.
Yeah, I'm not a native English speaker, so I just kind of go with the flow and hope that people understand me.
Okay. Right. In science fiction, whenever a star explodes, and they do that a disproportionate amount, there's always this sort of planar effect and it rips apart upwards and downwards. Is there any reality to that, and what shape is a star going boom?
Oh, that's a really good question. That was actually part of my PhD. Understanding the three-dimensional shape of core collapse supernovae was what I studied. So this kind of effect, I think, is just looks really good on video, but it stems from the mind of someone who's trying to give the audience a reaction more than science. Because a supernova, when it explodes, it's mostly spherical. It isn't spherical. It's a little bit oblong, like a kind of a burger or cigar shape. But it doesn't have that weird elongated plane. It's not homogeneous though. That's something that we know for sure. And if you see pictures of supernova remnants, so if you Google Cassiopeia A, I'll put that in the comments. Cassiopeia A. If you Google that and find the image, you'll see how blobby and everything it is, that it's not a nice homogeneous sphere. That's not an effect of the space that it's evolving in. That's an effect of the actual supernova. It's just that the elements are spread out in a messy kind of way and not evenly. But it's mostly round. It will be a little bit oblong because the explosion itself is messy. Now that's for core collapse supernovae. For thermonuclear supernovae, so the ones that come from white dwarfs that get too massive, the overall shape is mostly spherical. And if you look at supernova remnants of these supernovae, you'll see that that's the case. So if you Google Tycho's supernova, you can see that kind of supernova remnant. But the distribution of elements, so things like calcium, oxygen, all of that is a little bit messy. Because again, you know, the reaction that's happening in there has some randomness to it, and that's just the effect of nature. But that being said, about jets, nature can make jets, and it does make jets. It's a very rare case of a supernova, but it is a thing that you can get, and it's pretty dangerous if you were close to it. And that's where your star actually turns into a black hole. So most massive stars will turn into neutron stars, but if it's way too big, it will turn into a black hole. And if it turns into a black hole, shit gets real, because black holes are kind of the hoovers of the universe in a way. And so as the outer part of your star like falls inwards, it's going to start being like falling into the black hole actually. Now, because the star is rotating, because stars do that, and if it's rotating quite quickly, then that matter that's going into the black hole will actually settle onto a disk, an accretion disk. That's just something that's physics. It will happen. That's the most stable configuration if you are rotating. And that accretion disk also powers jets of light in orthogonal direction, so 90 degrees with respect to the disks. You've got your disk and you've got bipolar jets, we call them. And these jets are made of the most powerful light in the universe, gamma rays. Gamma rays will kill you if you're too close. And you can see these, you know, across the universe. They're incredibly powerful, but they're very, very narrow jets. And so to actually see them, you need to be in the right direction. They need to be pointing towards you. But we do see them, and we have a special name for these supernovae, for this phenomenon. It's called a collapsar because it collapses, I guess. And yeah, collapsars are pretty metal, and they make supernovae that are extremely powerful that some people call hypernovae, but some people are like, no, we don't call them hypernovae. Like, people argue about nomenclature, but yeah, hypernovae come from collapsars. You can try and use that at the next pub quiz.
Okay, we've got a couple more coming in. So why do two neutron stars spin around each other instead of just being attracted to each other like a couple of magnets?
It's just because things rotate around each other in space, because if you don't, you just fall in, right? So neutron stars didn't just happen. They used to be massive stars that rotated around each other. And there's nothing that's going to stop them rotating, really. So they're just going to keep rotating closer and closer and closer together. That's rotation is one of the ways that space stays together. So that's the reason that we're not falling into the supermassive black hole inside the Milky Way. That's the reason that the planets aren't falling on the sun right now. That's the reason the moon stays up in the sky, is because of rotation. Rotation is an amazing thing. Amazing.
Okay, and from Jess, who's actually my niece, so this is quite impressive for a 10-year-old. I understand there are two types of black holes, the stellar from a single collapsed star and the supermassive, which are much bigger and believed to be created from a series of stars colliding and are found in the center of a galaxy. Does every galaxy have a supermassive black hole at its center?
It's just a 10-year-old. That's unbelievable. Yeah. That's incredible. I don't get that kind of questions from undergraduates, so I'm impressed. Okay, absolutely 100% true. There are two types of black holes, basically, the stellar mass black holes and the supermassive black holes. Now, it is believed that all galaxies have a supermassive black hole in the center. These supermassive black holes are like millions, billions of times the mass of the sun. Now, where they come from is still a matter of debate. And actually, it relates to the first stars in the universe, because the first stars in the universe weren't like the stars we have now that are like 1 time the mass of the sun, 10 times the mass of the sun, maybe 100 times at most. The earlier stars were much bigger because physics. Long story short, I can explain that in detail if people really want to.
Just to check there, are you saying that a black hole or a star with a mass 100 times the sun is small?
No, sorry, the stars in the universe,
right,
that we have now can be up to 100 to 300 times the mass of the sun. The biggest one we know is 315 times the mass of the sun. A black hole won't get to that because these very massive stars lose a lot of their mass before they turn into black holes. And some of them don't even give you a supernova that leaves a remnant. They just disrupt themselves entirely because, they're too big. But yeah, no, we get black holes are like 30 times the mass of the sun. Those are the ones that we observe with LIGO, and these were created by stars, really big stars. Now, for the supermassive black holes, that's that's an ongoing topic in science, because we know quasars. So quasars are black holes in the center of a galaxy, and they're active. Actually, is Liam still here? I saw an attendee called Liam Grimmett. If he's still there,
I think he's gone into hiding.
It's fine. If he's still there, he's an AGN person. Active galactic nucleus. That's what these are. So it's where you've got the nucleus of a galaxy, supermassive black hole with matter stars around it.
We've got him talking in July anyway, so people can save the question for then.
Yeah, Liam's awesome. He's a statistician as well, so he's a bit of a nerd. Anyway, so these active galactic nuclei send jets, and if the jets are pointing at you, like really well aligned, it's a quasar because it's really bright and really extreme. Now, we see these quasars from really far back in time at the beginning of the universe. And so we're like, okay, so they were supermassive black holes at the beginning of the universe. How did they get that big that fast? How did that happen? And so one theory that I was looking at, I don't know, well, it's not my field, but I was reading a paper about that a few weeks ago, is that the first generation of stars were like 10,000 times the mass of the sun. So incredible. And these would create the seeds, so really massive black hole, the seeds that we need for these black holes to get this big, this quickly, and end up in the center of the galaxy. So it's still a matter of debate, but the main idea that I've seen is that we call them population 3. If you I'm just telling you because if you Google it, you'll find that term. Population 3 just means the first stars in the universe, the first generation. The first generation of stars before, when the universe was only hydrogen and helium, pretty much, before other elements were created, were very, 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 very massive, because the other elements in the universe are very important. They play, even though they don't make a lot of the universe, they play a crucial role in regulating how mass can accrete onto an existing star or a young star, and how stars cool and how their winds work. So yeah, they play a crucial role, and because there weren't any at the time, these stars are very, very different, and then they enrich the universe, and like now we have stars like the sun. The sun is a 3rd generation star or something like that. So yeah, excellent question. Wow.
Okay, so from Josh now, who's only a little older, could a black hole singularity gain enough mass by things entering the black hole so it outgrows the event horizon?
The event horizon grows with it, because the event horizon is the point where light goes in and can't come out. And so if you make a black hole more heavy, then the distance at which it attracts the photons extremely like that is just going to grow. Its influence basically is going to grow. So if you make a black hole bigger, its event horizon just gets bigger.
Okay, and I think this one's going back to spinning and why neutron stars spin around each other rather than just crashing together. Is it anything to do with conservation of angular momentum?
Exactly. That's exactly what it is. Absolutely. It's just that things have a rotation when they form, and that stuff gets conserved and carried away in some way when you have stellar winds or gravitational waves, and that's why things get closer. But yeah, conservation of angular momentum is key.
Yeah. And I think we're going to be on black holes for a little bit.
It's fine. Black holes are cool.
Do ring galaxies have a supermassive black hole at their center as well?
Ring galaxies? Do you mean like the sombrero?
George and Barbara, do you want me, if you'd like me to just turn on your audio, then just raise your hand and I'll let you ask the question yourselves.
Oh, yeah. It's just an appearance thing.
So, there we go.
Yeah, no, a ring galaxy, I think, is just like a ring of stars with no center to it. So I wouldn't imagine that they have a supermassive black hole or any black hole at the center.
I don't know.
But
so from what I'm seeing, baryon stability, galactic collisions.
I think they're caused by. I think they're caused by another galaxy passing.
It looks like collision. It looks like collision. So yes, there will probably be a black hole in there. So the picture I saw looked like an elliptical galaxy with a ring of young stars around it. Elliptical galaxies are really old galaxies with very red stars. Young stars are blue, red stars are old. So yeah, it looks like it's a collision of 2 galaxies. When 2 galaxies collide, their gas interacts and creates more stars, and that's where you get blue stars in these young galaxies. And so I guess that just by the way that it collides and the way that it settles, then these new stars would settle around in a ring. But there's no reason that the supermassive black hole would be disrupted by that. I mean, maybe, I don't think it could be slingshot out. It's way too big. Supermassive, like the galaxies, when they collide, their gas collides and creates new stars, but the things in it don't really interact that much because galaxies are mostly empty space. Like space is mostly empty space. Everything is mostly empty space. It's, you know, when you're in Star Wars and you see people dodging asteroids, that is not space. Space is not like that. Like it's things are so far away from each other. It's unimaginable. So galaxies don't, when they collide, their contents don't really collide either, apart from the gas, and then form stars. So I think the supermassive black holes would be fine. But you can ask Liam, because he's a galaxy person.
I can't say how reassured I am by the idea that supermassive black holes can't be slingshotted out of galaxies. So that's only the ordinary black holes then.
With the slingshot effect, when it's all conservation of angular momentum, right? So if you're slingshotting something, it's the less massive thing that's going to be slingshot. So you could consider something getting too close to the black hole and getting slingshot by it because it's so much bigger than everything else. But the actual black hole itself, it would probably have to be a very, very, very special condition for that to happen, if it happens at all. But I'm not a galaxy person. You can quiz Liam.
I'm going to ask Jess's question next and then come back to Alan's, because I think Alan's is going to change the conversation a bit. So
Okay.
Jess is again on black holes. If all objects make a bend in space or in space-time, do black holes do the same?
Absolutely, and that's why. So that's why we have this event horizon that nothing can come out of. It's like digging a well, basically. So if you imagine digging a well into the ground, light objects create a very small puddle, and black holes create a very deep well that nothing can come out of. Basically, they're just the densest thing in the universe. And so once you enter that well, there's no turning back. But they do, absolutely they do.
Okay, and how much use do you and or colleagues make of computers and software to model predictions about what might happen and what has happened already? That's from Alan.
That's my entire job. I call myself a computational astrophysicist because I use computers and software so much. I actually develop software. So it's such a big question, but yes, we can't do astronomy without software, and we can't do astronomy without models and computers. And the reason that is that we can't repeat the experiment most of the time. You just observe something in the sky, you can't touch it. All you can do is take a picture, or take several pictures over time, and that's it. And you're stuck with it. You can't go there, you can't prod it, you can't make it repeat. You're stuck with what you see. So what do? Well, you create a model in a computer, and you're like, I think this is what happened. Let's see how it plays out. And then you compare what you see in your computer and what you see in real life. If it matches, then you're probably on the right track. If it doesn't match, then you tweak it. You see what kind of physics you can add or change to reproduce reality. And that's the entire job of astrophysics. It's comparing your observations to your theories. And when we say theory, again, it's not I'm guessing it's this and it just came to me in the shower. It's physics. It's actual evidence, things that we want to be able to reproduce and test over and over again until we're like, okay, this is probably how things work. But yes, that's the process of science in general. But in astronomy, because you can't repeat experiments, you can just observe new objects. You have to have a strong component of theory and computer simulations to compare to what you see. So, and good question, thank you.
Just a mention from Alan, and I want to add my own mention onto it. He said that the first computer developed for astronomy purposes was by Charles Babbage, and I just want to mention another person who was somewhat involved in that with the first computer programs, who gets forgotten a bit more than I'd like, Ada Lovelace.
Yes, that's so.
Okay, and we've got another question. So you did mention galactic collisions, which sound terrifying. So how
we're
likely?
We're collide with Andromeda in 3 billion years, so we'll be fine.
I'll be fine by then, yeah. How likely are you to be hit by a bit of a galaxy when you collide?
I don't know. I'd have to do a back of the envelope calculation, but basically the probability tends to 0, basically. Especially if you're an individual star, an individual planet.
So if you're an individual person, you're probably okay.
Oh God, nothing's going to happen to you. You're fine. Even the solar system, what we call the cross section, is too small. Basically, it's how big an area you have to be hit with. So if you're trying to hit someone with, I don't know, a baseball bat or a cricket bat, the cricket bat has a bigger area, so you're probably more likely to hit them. But you know what I mean? So that's the idea of cross section. A solar system compared to the size of the galaxy, you're fine. But what will happen is that gas will compress because it's got much bigger cross sections, and collide and do crazy new things.
So probably not many stars colliding, but interesting things that we don't know about because they've not happened.
No stars colliding, but new stars forming. And that's really exciting because new stars forming means really powerful blue light, means new nebulae, so like the Horse Nebula, all of that stuff, that's created by young stars. So you get a lot more of these. You get supernovae because a lot of supernovae come from young stars, the core collapse ones, so you'll get a lot of things exploding. So a lot of interesting stuff, just not two stars colliding.
Okay. Right. And because it was in the headlines recently, Betelgeuse getting dimmer. What happened?
Betelgeuse. Oh, that's such a good question. So Betelgeuse is a really interesting star. It's a massive star that's reaching the end of its life. So it's really big and really red. So it's a red supergiant. Again, with the naming things in astronomy, super simple. And so what happened is that it started getting dimmer and dimmer unexpectedly at the end of 2019. Now, Betelgeuse is a variable star. It varies in brightness, but it was getting much, much dimmer than we're used to, and for a long time. And so we were curious as to what happened. So one of the hypotheses was that it was big sunspots. So a sunspot, which you may have seen pictures of, you've got the sun and you've got like little black spots. These are cool spots on the sun, and they're called by things like convection. So convection is a fancy word for a rolling boil. When you're boiling pasta and your water is going around making all these bubbles, that's convection. Now, in red supergiants, because of the way that they are, these convection cells are much bigger and they're gigantic. And so you can get sunspots that are extremely large. And so if you've got a really big sunspot, a really big spot that is very cool compared to the rest of the star, if you're cooler, you're less bright, and so the entire star is dimmer, and that could cause a change in brightness. And I mean, that's one of the reasons that Betelgeuse is variable in the first place. But that's not what happened. That is not what happened. And that was discovered, found, studied by Emily Levesque and Philip Massey, two of the biggest experts in the field. They actually looked at Betelgeuse, and what they found was that Betelgeuse temperature was the same. It really hadn't changed. So it can't be one of these sunspots that makes the whole surface cooler. It can't be that. What it was dust. And dust is really cool because we've talked about the origin of the elements. So supernovae create elements that are necessary for life as we know it. Kilonovae create elements necessary for our jewelry and life as we know it, because, rare earth elements, they're useful for technology. But these really old stars actually make most of the dust in the Milky Way, and they make a lot of the elements that we need for life as well, like oxygen, carbon. A lot of carbon comes from these stars, and that comes from this dust. So what happens is that these stars tend to pulsate, and so what can happen is that they basically pulsate and move some of their material in the envelope so far out that it reaches a distance from the star that is cool enough for the gas to condense into molecules, and for the molecules to condense into actual dust. Now, dust absorbs light, and so it's like putting a screen in front of the star. So if you're putting a screen in front of the star, it's not going to be as bright. And so that's what happened. A whole bunch of dust was created live right before our eyes and obscured the star for a little bit, and then moved away into space, and the star started getting brighter and brighter and brighter again. And so it created a bunch of dust that will probably go on to form planets in some other solar system at some point, which is pretty insane. And we saw that happen live. Space is metal. Space is so metal.
Okay. Last week, we had Jennifer Millard talking about radio astronomy, X-ray astronomy, invisible light astronomy. What's the impact of that been on studying supernovae and novae?
That's such a good question. So radio astronomy, it basically is very hard, by the way. I can't do it. Radio astronomy is very hard, but radio astronomy is very important if you want to, for example, detect the jets that I said you can't see if they're not pointed at you. So earlier I talked about the collapsar that creates those jets, and they're very narrow. And if they're pointed at you, you can see them. And if they're not, you can't see them. That's not quite true, because they interact with their environment, and you can see that in the radio if you want, if you can observe it there. So that's really useful for that. Infrared is great at probing anything dust, basically. So it can give you dust maps that are very useful for people in my field. But the most important invisible light we have in the field of massive stars and supernovae is the UV. Actually, it's the opposite side of the spectrum, because these things are so hot that they are very bright in the optical and the UV. So optical is the light that we can see, and the UV is the light that's bluer than what we can see, and that's really what tells us a lot about these regions of the sky. But yeah, invisible light is super important. Hubble is a key to UV observation for humans, because the UV is mostly absorbed by the atmosphere, right? That's why you don't fry anytime you go out. It's because most of the UV that the sun releases is being absorbed by the atmosphere. It protects us. The problem is that we can't observe it because the atmosphere is so good at capturing it. So we have to go into space and get away from the atmosphere if we want good UV observations. And that's what people do with Hubble, among other things.
I'm going to encourage people in the audience to start throwing their questions in, because I'm about to otherwise dig into the computer simulation, which is my field. And We'll start talking about procedural languages, functional languages, object-oriented programming, and so on. So if you want to ask about stars, now's probably the time to put questions in. But while we're waiting for those questions, I'd just like, because I think this is fascinating, a bit of detail about exactly what it is that you do now.
Okay, I'll try to summarize it, because I'm a bit of a bastard child. So right now I work with Janet Eldridge at the University of Auckland, and she has this amazing code called BPAS, which simulates a little universe in a computer. And you can follow the evolution of the stars in that mini universe over time, from when they're born to much longer than the current age of the universe. So you can predict the future, sort of. And so you compare that to observations. And so the main comparison that I want to do in my project is to look at gravitational waves and kilonovae and better understand what stars had to form to create those. Because, like I said, there are two neutron stars rotating around each other, but this system has to do two things. One, it has to survive two supernovae without being disrupted, which is crazy. And two, it has to be close enough after those two supernovae that it will merge within the lifetime of the universe. Because, they get closer because of the production of gravitational waves, but this isn't super efficient. So if they're too far away, they just don't merge within the current lifetime of the universe. So you need to balance these two things, which is difficult. And so that's part of my project, but we get distracted with a lot of other things because if you have a universe in a box, you can compare it to practically anything. And so I created a little pipeline called Age Wizard that tells you the age of a stellar population if you just put it into the pipeline. I like naming things stupid as well. Age Wizard is so fun. And I'm part-timer software developer, to be fair, because the code that my boss wrote is fantastic, but it's a lot of outputs, a lot of different data formats. And so to make it easier for observers to use, I've created a Python package that can help them do that very easily. That does a lot of the pre-processing and annoying binning and really annoying weight factoring and all of that stuff that you don't want to mess with if you don't know what you're doing. And my boss knows what she's doing because she wrote the code. So I put all of that in automated pipelines so people don't have to worry about it. You just do your analysis and it all works. So yeah, I'm kind of the middle woman between the observers and the theorists, and I like it.
Okay, so we have had a few more. Who was Schwarzschild, and what is his, or was his, I suppose is his equation?
So Schwarzschild, I can't spell it, but you can Google him. He was a physicist, and his equation, it's a pretty simple equation, actually. You can Google the equation. It's probably on his Wikipedia page. And if you give it just the mass that you're interested in, it will give you the radius that a black hole would have if it had this mass. So if you put into that equation the mass of the Earth, it will give you something that's about 2 centimeters across, so about the size of a marble. But he's done a lot of things. Like physicists tend to be known, physicists tend to be known for one or two things when they are, but they do a lot. And he was a great physicist. Hopefully he was a good person, but I don't know that.
We've actually had a question from Twitch, where you're being broadcast as well.
I didn't realize we had Twitch.
Oh, yep. We've got everything. We've got all of the platforms.
Wow. Okay.
All of the important ones. What are the most dangerous things for Earth from space? Let's ignore global warming and things like that. But from space, what are the most dangerous things for Earth? Probably
asteroids. So people talk about like, oh, supernova and gamma rays and blah, blah, blah. Like the chance that we're going to actually get hit with that. I would say that an asteroid is probably the most dangerous thing that can happen to us. Because there's the Kuiper belt, first of all, that's around the orbit of Pluto and a bit further out, and then there's the Oort cloud that's much further out, and it's full of debris, and that stuff sometimes gets slingshot towards the sun, and it's very unlikely, but asteroids could hit us. There's actually initiatives that keep track of near-Earth asteroids, NEAs, to make sure that they're not going to hit us, to keep track of their orbits and try and predict where they're going to be so that we can react. How we would react, I'm not sure. I don't know. I don't know if governments have plans to nuke asteroids if they come too close. I don't know what we could actually do, but there are programs that monitor those because it's realistically the most dangerous thing that could happen to us in the universe. Because something that hits us from the sky, if it's big enough, can have the same impact as nuclear bombs. And that's what killed the dinosaurs. So yeah, near-Earth asteroids, probably the biggest worry, or solar flares as well. If solar flares are too big, then the magnetic field of the Earth can't protect us, and that wouldn't kill us properly, but it could really disrupt our technology because solar flares are full of like nasty radiation that could disrupt us. And I think that that's also a big area of prediction. Solar physicists are a bit different. They're not really astronomers because it's a lot of like hardcore physics, and also their star is really close, so they get a lot of photons.
I can hear the horde of solar physicists storming to the door now.
Solar physicists, they annoy me. I've got a friend who's a solar physicist. I was like, oh, it's so hard to study my star. The signal to noise is really crap. He was like, just get more photons. And I'm like, I can't do that. They got so many photons that they have to have filters so that they don't get so many photons, they will destroy their detector. Anyway, solar physicists are a different breed. But they do really complicated physics stuff, magnetic fields and all that, and to try and better understand the cycle of the sun and when it's going to erupt so that we can, protect ourselves against these nasty radiations.
Okay. Right. So going back to the computer simulation, is the universe visualized in that computer simulation?
What do you mean visualized?
I'm assuming in some sort of visual way. Can you look at it, or is it data?
So it depends on the simulation. So for example, the Millennium simulation simulates the dark matter in the universe and all its filaments, and you can visualize that with a color map and kind of see the fractal pattern in the universe. With the simulation we have, it's all numbers, because that's what makes sense for us. And I mean, to be fair, it's always all numbers, and then it's whether or not you can apply a plotting device to it. But when you're actually simulating the universe, if simulating graphics is so computationally intensive, man, like there's a reason that gaming PCs are such beasts and have all of these GPUs. Graphics are one of the most expensive, in the computational sort of sense, things that you can do. And because it's already really difficult to simulate a universe in a box, we do things with just numbers, and we do things with really old programming languages that are really, really fast. So most of my boss's code is written in Fortran, which was debuted in the 60s or late 50s. I can't remember. Anyway, Google it. Fortran stands for Formula Translator. It's the stuff that is used to send people to space. It's the stuff that was on these big IBM machines that took an entire room and was programmed on punch cards. Fortran 77, I think, still had, when you coded it in a computer, you still had to leave like 6 spaces at the beginning of every line, because that's something that was a remnant of punch cards. I don't know, crazy things like that. But it's fast. It's just really, really fast at doing all of these incredible calculations and all of this physics that you need to do. So you can visualize some of these things, but that's pre-processing. That's something you do afterwards to either get, oh, my boss actually, I just remembered. Sorry, I get excited about space and computers and things. My boss has an amazing bloody video. Actually, that's a great visualization. It looks so out of this world. So she's took all of her models, and she's done a video that's about 20 minutes long, 10 minutes long if you watch it on twice the speed. And it shows you all of the models for all of the masses of the stars and how they evolve. And so you start with a star and it's tiny, and then it gets bigger. And then there's a red circle, that's the supernova, that's the ejection of the envelope, I think, or the supernova. And you can, and so it's color coded, and it looks abstract. But it shows you exactly what happens, and you can see the novae and the supernovae. I'll see if I can find it and put it in the comments if you guys want to check it out.
Yeah, or if you can't find it straight away, if you just send us the link later, we'll retweet it and share it out. We've had a few now, which are on the same sort of doom and gloom Armageddon theme, so I'm going to group them together. There's the one from Twitch again, which is, can we really predict when an asteroid will hit us, and can we really do something about it? We've got mention of being really scared of cosmic rays in someone's youth, which was knowing the person a while ago.
Yeah, don't worry too much about cosmic rays. They hit us all the time, but the atmosphere does a really good job.
And how close would a supernova need to be for it to have a bad effect on this planet?
I'd have to do the back of the envelope calculation. To be fair, I should have done that, because I get that question often, and every time I'm like, I'll do the calculation later, and then I don't. It would depend on the supernova. It would depend on the supernova, because some of them are more powerful than others. The ones with the gamma rays are more powerful, and the gamma rays are really deadly and things. So if these were close and pointed at us, they wouldn't need to be as far as others to be problematic. So I'll do a back of the envelope calculation, and I'll put it on my Twitter or something when I've done it. So yeah, stay tuned for that. I really need to do it. As for cosmic rays, yeah, they're problematic if you're in space. If you're in space, that's why space exploration is such a tricky endeavor. I mean, there's loads of tricky things about space exploration, but radiation is a bad thing that can actually affect you and give you cancer and stuff. Actually, if you, I remember Chris Hadfield is my favorite astronaut, little known fact, and he talks about when they go to sleep in the space station and they close their eyes and the lights are dark, they can see streams of light sometimes, and that's cosmic rays interacting with their eyeballs, and that's really awesome to me. But on Earth, you're fine. The atmosphere is a beautiful blanket, and the sun is a deadly laser. If you know that reference, you know. And the atmosphere does a great job at protecting us. So don't be too scared of cosmic rays. As for asteroids, the question about asteroids, if we can see them, yes, we can predict where they go, because it's gravity. And we're actually really good at calculating gravity. Einstein and Newton did a great job at giving us all the equations that we need. If we can send people to the moon, if we can slick shot rovers to Mars or to Mercury, we can predict the location of asteroids. Actually, we have to, if we want to observe them, because they move so fast, you can actually see it move, and you have to move the telescope really fast, and you can see it move on the picture. So you need to predict where they go in order to be able to observe them. So we can. The tricky thing is, do we see it soon enough?
Okay, I'm going to do one that's possibly controversial now. Do you have an opinion on the Starlink satellites?
You know what they say? If you can't say nice things, don't say anything at all.
And then the continuation for that was, if so, what is it?
What is it? Oh, yeah.
What's your opinion?
Here is the thing. Elon Musk is a businessman, and he's very good in making Musk Bros believe that, he does that for humanity when he does it for money. And it's also a stupid plan, because Starlink internet is going to be so expensive that the people he said, well, it's not a stupid plan. He knows what he's doing. But the people who believe that it's for Africa and people who can't access the internet today are delusional in my mind. Because, and you know what? At me on Twitter. I don't care. At me. Delusional in my mind, because it's going to be so expensive to get that kind of internet that these people can't afford it. And Elon Musk isn't going to give it away for free, because he wants money. He's a billionaire. Eat the rich. These people are problematic because they take matters into their own hand without consulting the public, without consulting scientists. They just have so much money, they can do what they want, and they're given free range to do it. And I don't agree with that. I think we should do things collaboratively, and he's not doing that. So yes, that was my 2 cents.
I remember reading, I think it was a few years ago now, about another satellite internet project, which was somewhat different, where it was designed to orbit over Africa, and it wasn't two-way communication. It was purely, you can connect to it with a cheap satellite dish, pull down Wikipedia, pull down reference material, pull down plans to build water stills and things. I'm just trying to find the name of it now, but I thought that actually got launched as well quite a while ago, so less marketing involved there, but obviously that didn't work in its favor.
No. And when Elon Musk says, I don't do marketing, I don't do ads, I'm like, sorry, you sent your own car into space, as if that wasn't a marketing ploy. Come on, how dumb do you think we are? Anyway, I will stop now.
I think that answers the question about your opinion on it. Let's go for a different one, less controversial, definitely less controversial. Do you think governments actually have plans for solar flares? And if so, are they better than the ones they've got for pandemics?
Bless, that's such a good question. I don't know. The answer is I don't know, because I don't work with governments. I guess it depends on what astronomers told them and how much they listened. The response for pandemic is when it is. Again, that's the problem with we'll not go into that. Less controversial, my arse.
Right. Are there less controversial questions?
Are you asking me or asking the
public? I'm asking everyone, or you, if you want to ask a question.
I'm not asking a question to myself.
Right. In that case, I'm just going to wrap up with one last question, which is, if there's one thing that you would like to clear up that people get wrong about Novae, and I mean not necessarily the public, but also astronomers, astrophysicists, physicists, chemists, anyone, one simple question that people get wrong, what would you like to correct?
Betelgeuse isn't going to go supernova anytime soon. Stop asking us. Sorry to be disappointing. Yes, you can see it. You will be able to see it with your eyes, but you won't be there. So yes, it will be visible in the night sky, but Betelgeuse isn't going supernova. It just made a bunch of dust, which is just as cool in astronomers' minds, but sorry, that supernova isn't happening anytime soon.
I think the fact it's making new planets probably counts as fairly cool, even if it's a way off.
Yes.
Right. After that, it's just a huge thank you for being with us.
Thank you so much for inviting me. That was so much fun.
We're getting some good feedback already. So yeah, your enthusiasm is infectious. I'm probably going to go out and stargaze in a bit now, which I wasn't going to. But yeah, definitely just a huge thank you for that. We hope you've enjoyed it. Obviously, this will be up on YouTube and various others, so people can watch it again. You can reference it. You can send it to friends, family, advertise us. We do marketing, but we are non-commercial, so it's a trade-off.
Thank you so much for having me and your questions and everybody's questions. Your questions were so great.
And if you have more questions, Eloise is on Twitter and you can bombard her with them there.
You can do that. I will answer.
And
I'm always procrastinating, so go ahead.
Let me just set up and I will talk about what we're doing, not next week, but we are doing a special event coming up on Saturday where it's another person really enthusiastic, but all of May has been astronomy. So we're taking a break from astronomy and we're going to be covering sharks with Jada Elcock, and it's going to be an earlier event to make up for this being a late one on Saturday at 5 p.m. Do check out Jada's Twitter as well and do join us for the event. It's going to be fascinating. I have been pre-warned that there are sharks which can leap 30 feet in the air, and there is a slim chance if you're swimming they might land on your head.
Wow.
I've been told it's unlikely. It's probably actually it's probably more likely than an asteroid landing on you. So yeah.
Yes.
Worry about sharks rather than asteroids, and
Death by shark.
Join us for that. And thank you all for coming. I'm going to end the kick you all out of the studio audience now. Thank you again, Eloise. Thank you, everyone else. If you want to rapidly click your raise and lower hand button, it does look a bit like applause.
Thanks, everyone. Bye.
Good morning.